All right, thanks Josh and Helen and everybody at Crowd Supply Teardown for this opportunity. Um, so while we wait for people to walk in, I will challenge anybody to derive that first equation that you see on top of this page using trigonometric identities. And if you can successfully derive it and explain how, you'll get a prize at the end. Okay, so this is space mission design on a napkin or an envelope. I've been working in the space industry for many, many years and also had a short stint in the unmanned aerial vehicle industry. So if you took high school math, you've seen all the equations I'm going to show you before, so hopefully I can add some context to that. Couple things I did not have time for is Keplerian orbit propagation and subsystems. But Andrew Greenberg and the ORSAT team can tell you all about satellite subsystems. I'm going to focus on systems engineering, focusing on this question of how many satellites do we need? Okay. I'm not going to repeat this introduction because it's in the program, but before I proceed, I do want to pass around a couple of props. Here I have two topographic maps, one from 1962, one from 1997. They're both of the same area. And what I'd like you to look at is the information in the bottom margin on the left side. That will come up in the presentation. And please keep the maps together so that everybody can see the two maps side by side. The second prop I'd like to hand out is this magnetic compass. And what I'll ask you to do is look inside the round dial of the magnetic compass and study the features of the magnetic compass, because we'll be discussing that over the course of this presentation. Can everybody hear me well? Okay, good. Okay, so this is about the time in the presentation where the presenter usually says, I promise I'm not going to show you very many equations. And it turns out that's actually true. I'm not going to show you very many equations, but we will dive very deeply into those equations and how they're used in real space missions. So get your calculators ready or your slide rules, and you might want to have a sheet of paper to write on. One of the simplest but often most costly mistakes we make in engineering is failure to maintain consistent units. Early in my career, I worked on a space launch mission where the upper stage tumbled out of control because two pieces of software written by two different contractors passed data with different units without proper unit conversion. That was a $1 billion mission loss because units were not converted properly. So in your scientific calculator, most scientific calculators that you use angles in radians or degrees. So I want you to try out on your calculator, make sure you can switch between radians and degrees, and that you know which units you're using. Also look for your trig functions, sine, cosine, and tangent, as well as the inverse trig functions, which you typically access by a second function key. Okay, let's check our angle units. Who's actually going to do this on their calculators? Okay. To check your angle units, enter 1 and enter the key combination for inverse sine. If you get 90, your calculator set to degrees. If you get 1.57, your calculator set to radians. If you have a symbolic result, press the enter or equal key to evaluate to a numerical result. All right, so now we're going to review basic plane geometry from high school. We have an XY coordinate system, X horizontal to the right, Y vertical up toward the top of the page. 0 degrees is to the right. And as we increase the angle theta, this vector r moves in a counterclockwise direction. Now, this vector r represents the point that's in Cartesian coordinates x, y. But I'm also representing polar coordinates here. X equals cosine theta, y equals sine theta. So you can represent this as r comma theta as an alternative to x comma y. And in real life, we actually use both coordinate systems quite a bit. There are a lot of situations where polar coordinates or circular coordinates are a lot more convenient than Cartesian coordinates. So in practice, you do need to know both. All right. Note these numbers here. Let me change to what might be a more interesting angle here. Note the value of theta, x, and y. On this next plot, you're going to see those exact same numeric values, 115 degrees, x equals minus 0.4, y equals 0.9. Okay? But you see that the position of the vector r on this plot is different from its position on the previous plot. Why is that? Different, did you say different origin? Okay, you're on the right track. I think you meant different axis orientation. So the x and y axes are swapped in the geographic azimuth coordinate system. We first talk about the north, and then the second coordinate is east. But the numeric values are the same. I'm going to go down here and show you the two plots together and activate this slider. Whoops. Okay, so as I change the angle, what do you notice about the two plots? One's going clockwise, one's going counterclockwise. That relates to the right-hand rule. In real life, sometimes we make a choice to follow the left-hand rule, or we have to make other choices, awkward choices, to accommodate the right-hand rule. And we may run into an example of that momentarily. So in these plots, I started with the polar coordinates r and theta and calculated x and y using the sine and cosine functions. If you wanted to go in reverse, start with the Cartesian coordinates and get r and theta, how would you do that? Arctangent. Okay, we have somebody who remembered their math. Very good. So we're going to start going into practical applications. One of the most common calculations done in space missions or UAV missions is direction and range from the location of your UAV or satellite to the location of a point of interest. Often that point of interest is a point that you want to take an image of. And this is actually one of the projects I worked on in my last job when I first started. So in the following slides, I'm going to use the subscripts S for self, or your position, your UAV, your satellite, and the subscript LM for the landmark position. And we're going to look at the Cartesian coordinates and do some calculations with those. So we want to find the horizontal distance from your location to the landmark, the bearing or geographic azimuth, and the elevation angle. So anybody here skied at Mount Hood Meadows? All right, very good. So we're going to, as our landmark location, we're going to use Mount Hood, indicated on the upper left. And for our own location, we're going to use the Hood River Meadows HRM parking lot. This blue grid here is a 1,000 meter grid. So just by looking at this, anybody want to estimate the approximate geographic azimuth from Hood River Meadows to Mount Hood? Go ahead and shout it out. Northwest. How about in angles, degrees? 270 plus 45, thank you. 315, right? 315 or minus 45. Does anybody want to try to estimate the range or the horizontal distance between those 2 points? Remember, those square boxes are a 1,000 by 1,000 meter grid. Oh, zoom out. Okay. Yeah, unfortunately, I can't. Square root of 50. Okay. Thank you for that guess. And I was hoping you would all be writing some stuff down here, but if you're in the mood, I encourage you to actually write down these coordinates because I'll talk you through the calculations. So on the top, we have the east coordinates, and on the left margin, we have the north coordinates. So I encourage you to go ahead and write down the east and north coordinates and just eyeball this and make your best estimate of what the east and north coordinates are. Okay, nobody uses pen and paper anymore. Okay, if anybody wants me to go back, let me know. Otherwise, I'll give you a chance to look at the coordinates of Hood River Meadows. Oh, yes. At this point, I'll encourage you to actually estimate the coordinates, the north and east coordinates, or east and north coordinates, and write them down, because I'm going to actually run you through the azimuth and range and elevation calculations. Okay, does anybody want me to go back? Okay, I'll go back. Is anybody still on this slide? Okay, I'm going to go back for those who want to go back to Mount Hood. Okay, does anybody need more time? All right, moving on. So these are the coordinates I wrote down. If you're going to do the calculations, I encourage you to use your numbers. But you might want to compare your numbers to my numbers. I would say if you're within 100 meters of the numbers I got, that's probably good enough. If you got within 10 meters of my numbers, you're either really good or you got lucky. So these are the absolute coordinates. So the 0, 0 coordinate is an origin defined in what we call the UTM coordinate system. So this grid is the Universal Transverse Mercator Grid. Anybody served in the military and worked on artillery? No artillerymen here, huh? So in the military, we call this the MGRS, the Military Grid Reference System. The notation is slightly different, but the numbers and the grid system are the same. So we want to go from at the absolute coordinates to relative coordinates. What are the coordinates of Mount Hood relative to my location at HRM? So we do a vector subtraction. We take the destination vector, R sub landmark, minus the origin vector, R sub S, and you can do that component-wise. You take the east component of your landmark, subtract the east component of your location, and do the same for the north coordinate. So the next question is, what is the horizontal distance from your location to the landmark? Okay, so I'm going to note that capital D sub H, and it's simply the square root of the sum of the squares of the difference in the vectors. So I have two different formats here. I have an algebraic format where each component is squared inside the square root. But I also have a vector notation format where I use the vector dot product inside the square root. Under what circumstance would the vector notation be a lot more convenient to use than the algebraic notation? Okay, why even bother with the vector notation? Okay. Let me give you a more practical application. How many dimensions are we working in now? 2 dimensions, right? When we go to 3 dimensions, what happens to the algebraic notation? We're going to add a term inside the square root, right? And what happens to the vector notation as we go to 3rd dimension, 4th dimension, 5th dimension, etc.? The vector notation stays unchanged, so no matter how many dimensions we're working in, this vector notation doesn't expand, whereas the algebraic notation does. Okay, has anybody calculated the horizontal distance? Okay, hold that thought. And this is the azimuth equation. To get the azimuth, we use the arctangent or the inverse tangent function. Conventionally in mathematics, we do the one component, east or y, and divide by the other component, the adjacent component, north, and then we take the inverse tangent. But has anybody programmed the arctangent or inverse tangent in a computer before? Okay, so most computer functions will not have you do this division first. Most computer functions will have you enter the two components separately, and the computer will do the computer program will do the, or computer language will do that division internally. Why is that? Yes. That's right. It's ambiguous which quadrant. So you might have a situation where your delta E is negative and delta N is positive, or you might have a situation where your delta E is positive and delta N is negative. If you do that division first, you get the same argument into the arctangent. So I believe it's 180-degree ambiguity, but what computer software libraries do is they resolve that ambiguity by having you enter the two components separately, so that software library knows which component was the negative one. Okay, so let's go through some solutions. This is my code, and here I show it in a little better formatted way. What did we calculate for the horizontal distance? 7,110. And did anybody successfully calculate the azimuth? 312? 312? Okay. Oh, so you might have had slightly different numbers, which is fine. So what I got was 318, or negative 42.06 degrees. I went to caltopo.com. I should have done this first. Maybe I'll just use my, Teardown presenters. Here we go. Does anybody know the password for Teardown presenters? If not, I'll just go to my phone. Okay, I think I'll just move on for now. So when I make my measurements on caltopo.com, I get a true bearing of 41.4 degrees, whereas I measured 42.6 degrees. Why is there a 0.96 degree difference in the bearing? The world is not flat. That is the underlying explanation, but can you relate that more directly to the map? Right, the map projection projects a flat surface onto a spherical surface, so there's some distortion there, right? Did anybody notice anything about these grid lines? Say it. The grid lines are crooked, right? And the grid lines are crooked because we took a Cartesian surface and projected that onto a spherical surface. So in the middle of this UTM section, these are going to be perfectly straight. But along certain outer edges of this UTM projection, it is going to be distorted. So did anybody see the indicator on the map that tells you how much distorted it is? Okay, did anybody see? Let's see. Did you guys notice these in the bottom of the map? So if you look on the bottom left margin of the map, you'll see these declination indicators. So what are the three things that are shown on each of these declination indicators? Yes? Geometric north, magnetic north, let's call that geographic north or true north. The North Star would be true north or geographic north. MN is magnetic north. Anybody want to guess what GN means? Greenwich, that's a good guess, but not quite. So GN stands for grid north. So you can see the angles listed next to these. What's the angle between true north and grid north here? Okay, 56 minutes, right? That may not be clear, but what this is showing is that the angle from true north, represented by the star, to grid north is 56 minutes. And of course, there's 60 minutes in a degree, and that turns out to be about 0.9 degrees, right? So if you go back to this comparison, where did I have that? So my measurement differed from the CalTopo measurement by about 0.9 degrees. And that's because when I take this measurement on CalTopo, it's taking that measurement relative to true north, whereas because I used the UTM coordinates in this 1 degree tilted grid, my resulting azimuth angle is going to be off by 1 degree compared to what CalTopo calculated. Now, was our calculation wrong? No, our calculation wasn't wrong, but if we're going to communicate our calculation to my hiking buddy, what do I need to tell them? The difference, right? So we can tell the difference. I can say there's a 1 degree difference between my angles and those in true north, or if your buddy knows as much as you do, you can just say, my angle is taken relative to grid north, and then you can let your buddy make that translation. Okay, what's the other declination that you see in this declination indicator? And why did I show you 2 different versions of the same map, one from 1962 and one from 1997? Magnetic north has drifted, right. So was anybody in Boy Scouts? Did anybody learn map and compass navigation in Boy Scouts? Okay, so in Boy Scouts, what they teach is, to keep it simple, when you get your map, the first thing they tell you to do in Boy Scout navigation is draw magnetic north lines all the way across the map. So draw these 20 degree or 18 degree tilted magnetic north lines all the way across the map. That way you can navigate relative to magnetic north with your magnetic compass, and you don't need to make any adjustments. If you try to use your compass with true north or grid north, your needle's pointing to magnetic north and your lines are true north. So you need to add or subtract readings when you go from your compass to your map. Now, the compass I've been passing around has a feature that simplifies this. Did anybody notice that? Okay, I can't really display it up here, but inside that dial there's what's called an orienteering arrow, and the way we use the compass is we put the magnetic needle inside the orienteering arrow, and if you do that, the numbers on the compass line up with the directions. But the orienteering arrow, if you look carefully, who has the compass? Okay, look inside the dial. What angle is the orienteering arrow pointing at? So there's an arrow that's tilted, and there's an adjustment so that I can actually program this mechanically into that compass. Do I not have a... Would somebody run out and ask for the presenter's password? I will need that eventually. This one? Oh, crowd supply station.
Okay. Go ahead and try. I'll stand until it works.
Good. It's trying. Okay, thank you. So we're going to talk about geomagnetic models now. So this plot shows the Earth's geomagnetic field lines. It's a little busy because it's showing you both the potential lines and the field lines, which are orthogonal. So I'm going to go back and show you a map of magnetic declinations. Whoops. So this is a contour map showing the magnetic declination of every point on the Earth. So you can see that where we are now, it's about 15 degrees east, and I don't think you have it on the map, but here, this is from CalTopo. This shows the current magnetic declination as 14.4 degrees east, and I believe that's about consistent with what we see on the map here. So I'm going to exercise a computer model that calculates the geomagnetic field. So I have a computer function here, IGRF, for International Geomagnetic Reference Field. So I entered the year, which I've entered as 1997. This is the height, latitude, longitude. And when I evaluate that function, I get a vector. The magnitude of this vector relates to the magnetic field strength. I forget what units they are, but the components of the vector indicate the direction of the magnetic field lines. So I'm going to, and note that this has 3 components, and these are north, east, and down coordinates. So this tells you from your location which direction north, east, and down do the magnetic field lines follow. And when I do that calculation, the magnetic declination is 18.12 degrees east. This is in 1997. But there's also a magnetic inclination. The magnetic field lines are not horizontal here. The magnetic field lines are actually tilted minus 68 degrees. So it's tilted quite a bit downwards. Now, who has the magnetic compass? Okay. Is the magnetic needle being tilted downward? Oh, it is, okay. There must be a defect in that compass. But typically, the magnetic needle of a compass is going to be relatively flat. It's not pointing 68 degrees down. Why is that? Okay, the needle can freely spin in the horizontal. Oh, you're saying it's constrained, so it. Okay. Okay. So I put a little caveat. Well, I should have put a little caveat in there. So far, we're just considering the magnetic field, right? What other forces are acting on that magnetic needle? Gravity, right. So in fact, with a very simple magnetic compass, a lot of them have the compass needle weighted unequally. One side of the compass needle will be slightly heavier than the other to counteract the small effect of that magnetic inclination. But what that means is a compass has to be designed for certain regions of the Earth. So for a very simple compass, you might see that you have to order a northern hemisphere or southern hemisphere specific model. A very fancy compass has a mechanism that will automatically compensate that. And we call that a compass that has a global needle. Now, the compass I've been passing around does in fact have a global needle. Did anybody notice the mechanism that might cause the needle to always be flat even as the magnetic field inclination tilts up and down? Okay, so I'm not going to go into that here, but if you want to look at that compass later, please do. So the geomagnetic field or the geomagnetic model is one aspect of the space environment. Now, as humans, we live in the terrestrial environment where we breathe air composed of nitrogen, oxygen, carbon dioxide, et cetera. We live within a certain pressure range and temperature range, but satellites operate up in space, and they experience a somewhat different space environment. The geomagnetic field is very important. For low Earth orbits, we have atmospheric models, we have celestial bodies, and we have gravity. Now, is gravity uniform everywhere on the Earth? No. So here is an image of gravity field anomalies. So this contour plot shows the local variations in the gravity field. And depending on where your satellite's operating, these local anomalies can be more or less different. So if your satellite is a high altitude satellite, 36,000 kilometers above the Earth, compared to a satellite that's very close to the surface at 500 kilometers, which satellite is going to be more affected by the variations in the Earth's gravity field? The closer one, right? And if your satellite is operating far away from the Earth, what other gravity forces can affect its motion? The sun and the moon, right. So in low Earth orbit, we worry more about these local variations. At geostationary orbit, we worry more about the effect of the sun and moon's gravity. In modern times, since human spaceflight, we've started introducing space debris into the space environment. But long before human influence, there was the micrometeoroid environment. Okay, so far we've only talked about azimuth. Let's talk about height. So keep the horizontal distance in mind, about 7,110 or 11 meters. Now let's take a look at the height of Mount Hood. Let's call that 11,240 feet. and the height of Hood River Meadows is 4,523 feet. The conversion factor, multiply the difference by 0.3048, and you'll get the difference in meters. And how do we calculate the elevation angle? If we're down at Hood River Meadows and Mount Hood is so many meters higher, how much do we need to tilt our camera up? We call that the elevation angle. Okay, and this is the equation for the angular elevation, inverse tangent of delta the vertical displacement over the horizontal displacement. Now, is this a new equation? It's the same equation we saw for azimuth, right? We just use different arguments to the equation. Okay, so here's a graphic. As you reduce the vertical displacement, your angle obviously decreases. And as you decrease the horizontal displacement, the angle is going to increase. So how many unique equations have we used so far? Okay, we have this inverse tangent equation, and we have this sum of the square roots equation, right? Oh, where did that go? So it turns out we use these equations a lot, and you know, I've taken more advanced math classes, but I think I use these equations a lot more than any of my more advanced math. Okay, and slant range, where have we seen this equation before? Oh, so delta H again is horizontal displacement, delta V is the vertical displacement. The 7,110 meters, what did that represent? The horizontal distance, right? So this equation will give you the slant range, and in terms of a triangle, what is the slant range in terms of a right-hand triangle? It's the hypotenuse, right? So here's a question. Can you figure out the slant range equation in 3 dimensions? How would that look? There'd be one more term, right? In fact, this delta H, that was calculated from the square root of the sum of the squares of delta X and delta Y. If we just expanded the equation, you would just have the square root of delta X squared plus delta Y squared plus delta V squared. But it's the same equation, right? Okay, so let's go into a space mission design exercise. Nobody told me how much time I have, but how many satellites do we need? As a systems engineer, that is one of the first and most common questions that's asked. The higher-ups want to know how many satellites do we need to pay for? What additional information, what additional assumptions or knowledge do we need to answer that question? Yes? Distance from the sphere or the height of the satellite, yes? The angle of view of your sensor, yes. Those are the 2 principal things we need. Let's see. So in systems engineering, we ask, what is the desired coverage area? What part of the Earth do we want our satellite to see? And what is the desired revisit time or the number of folds of continuous coverage? And that's related to the sensor field of view and the maximum slant range or minimum elevation angle. Does anybody here know GPS? I know one person does. So for the global positioning system and most global navigation systems, what is the desired coverage area for GPS? Hint, it's in the name. Global, right. So GPS provides navigation everywhere on Earth. And for GPS, what is the desired revisit time or number of folds of continuous coverage? Folds of continuous coverage means how many satellites do you need in view? 3 is a good guess. There are people saying 4. 3 is a very good guess. And the 3 dimensions you're thinking of are what? Triangular. Okay, so you're probably thinking, if I want 3-dimensional position, if I want to know my XYZ position, I need 3 measurements to calculate 3 unknowns. But the way GPS works, there's a 4th unknown that needs to be corrected for. And who wants to say that? I'll give that to time, right. So for GPS to work, the time on your GPS receiver has to be synced to the time on the clock. you can't directly sync that, but there's some clever tricks that are done so that your GPS receiver learns or calculates what its clock error is. And after correcting for its clock error, it can accurately calculate the X, Y, and Z. So let's see. I suspect I'm running out of time, so I'm going to, I'm sorry? Is there different clock error for different satellites? And the answer is yes. And actually, there's clock errors on each individual satellite, but there's also a clock error within your GPS receiver. So the clock error on the satellite, that's monitored on the ground station. So the ground stations are monitoring the clocks on the satellite, and the ground station's constantly sending up corrections to the satellite, telling the satellite what its clock error is. And the satellite, when it sends the information down to your receiver, it's incorporated its clock correction that was given to it from the ground. And then your GPS receiver uses some clever tricks to calculate what the receiver clock error is. And that all goes into giving an accurate three-dimensional position. So for this example problem, we'll consider a satellite orbit at 500 kilometers and a sensor field of view with a half cone angle of 45 degrees away from nadir. So nadir is the down direction. So from the satellite or UAV, if you're looking straight down, that's the nadir direction. That's important because the down direction gives you the shortest distance to the ground. So sensor field of view is often measured as off nadir, so we'll consider 45 degrees off nadir. We're going to use some flat Earth approximations, so we're going to start with circumference of the Earth. So let's calculate circumference of the Earth. 2 pi times the radius, which is 6,378 kilometers. So I'll let you do that calculation. So why do I need to know the circumference? I think I glossed over part of this. For our mission design problem. So our mission is going to be, we're going to monitor the North Pole. We want to monitor Santa Claus's activities to make sure he's progressing to deliver Christmas gifts on time. So our geographic coverage area is just going to be the single point at the North Pole. Our temporal requirement is going to be continuous coverage of the North Pole. So we never want to lose sight of Santa Claus at the North Pole. How many satellites do we need if our satellites are at 500 kilometers altitude and sensor field of view of 45 degrees? 500 over the surface. Good question. And in our calculations, we'll often add the Earth's radius and get the radial distance of the Earth. Okay, so why do we want to know the circumference of the Earth? So for anybody who's not familiar with orbits, a low Earth circular orbit is basically going to go in a circle around the Earth at a fairly constant rate of 7.1 kilometers per second. And for our purpose, we'll arrange our satellites so the satellites, as they go around in their circle, are crossing over the North Pole and the South Pole. But if we want to always have one satellite in view of the North Pole, how many satellites do we need? The reason I ask about circumference is whatever ground distance that a single satellite can see, we need enough of those satellites so that those coverage area is continuous when you connect the various satellites. So the next part, we're going to calculate the horizontal coverage distance of the sensor cone. So from the nadir direction at 500 kilometers, we have a 45-degree sensor cone. What is the diameter of the circle projected on the ground by that cone? So here's a graphic. Of course, with 45 degrees, it's pretty simple. It's going to be equal to the satellite's height. So our coverage radius is 500 kilometers. Our coverage diameter is 1,000 kilometers. So if one satellite can cover a 1,000-kilometer diameter on the ground, how many satellites do you need for a continuous circle of coverage around the Earth? 40? Okay, I hear 40 here. And that's why we needed this circumference of the Earth, right? So what we did was we took the circumference of the Earth, which is 40,000 kilometers, and we divided that by a single coverage circle diameter of 1,000 kilometers, so we get about 40 satellites. And when we do that division, I actually get 40.1, so if we had 40, we'd have a slight gap between at least 2 satellites, right? So I'm going to round up the number of satellites to 41 kilometers, and that tells me the spacing of the satellites. If you take the satellite subpoint on the ground, those have to be spaced 977 kilometers between consecutive satellites. Now, how confident are we in this number of 40 or 41? Okay, do we think, are we confident that that's the correct number? No, why not? What's the principal error we're not accounting for? Non-spherical, right. We're making a flat Earth approximation. Do you think 41 or 40 is higher than the true number or lower than the true number? Higher than true number, right. Okay. So if you can visualize the difference between, actually we'll go ahead and do that now. So this is 47 satellites around the flat Earth. So when we zoom in, you can see that their coverage circles overlap by about this much. So I think we answered this question already. Another question is, what are the limits of this approximation? When does this approximation, the flat Earth approximation, become unreasonable? I think I'm going to skip over that for now. This is the visibility triangle. Did anybody succeed in deriving this equation? No, okay. You need to use the law of sines. I'll give you that hint. So I'm going to try to zoom in on here. Whoops. So this is that visibility triangle projected onto the curved Earth. So you can see that slight curve. And you can see the elevation angle is 40.3 degrees. If this were projected on a flat Earth, what do you expect that elevation angle would be? 45 degrees, right. I'm expecting one more here. Okay, either I'm forgetting or I'm missing something, okay, so the other important parameter here is to get a clear answer, it's convenient to work in terms of the Earth central angle. So instead of using the sensor half cone angle, in a study, what I do is I immediately calculate this theta, the Earth central angle. And using this equation above, these two equations above, we can calculate what theta is. So instead of working with 3 parameters, two parameters, so we were working with satellite height and elevation, or sensor half cone angle. If I use these two equations, I can boil it down to a single theta. So Earth central angle is 4.69 degrees. So that's the angle measured from the center of the Earth rather than from your satellite, measured to the edge of your coverage cone. So theta is half of the coverage circle, so twice the coverage circle would be double 4.69, right? So what's double 4.69? So using this number, can you calculate the true number? 38, right? So what we did was we took 4.69 times 2, what is that? 39, okay, very good, 39. So 4.69 times 2. Measured at the Earth central angle, a single satellite will cover 9.38 degrees of Earth central angle. If you take 360 degrees around the Earth circle divided by 9.38, you get 38 and a fraction, which you round up to get 39, right? So 39, and with the flat Earth approximation, we guessed 41. Was that a useful approximation? Sure. And if you know that the flat Earth approximation is going to give you a slightly high number, that's even more useful because You know you definitely don't need more than 41. You need slightly less than 41 probability, and we confirm that with this calculation. Okay. Josh, how much time do I have? 5 minutes. Okay, thank you. Okay, I think I'll use this 5 minutes to take questions. Yes?
Wouldn't you need some extra satellites in case some drift or like fall or something?
Would you need extra satellites for various reasons? Absolutely. So this is just an academic exercise to give us the theoretical minimum number of satellites. We do launch extra satellites. In fact, the nominal constellation for GPS is designed for 24 satellites. In practice, we've been operating with 31 satellites. And there's also what's called a sparing strategy. Where do you locate the extra satellites to make them most useful as backup spares? Thank you. Excellent question. Next.
So earlier you had like a magnetic north calculator and such that you're showing in code. What happens if you try to predict the future like that? Put in a year that happens.
Okay, what happens if you enter a future year into the magnetic model code? To some degree, those magnetic models do predict the future because they have to be useful. Of course, the further they predict into the future, the more susceptible they are to error. I'm not a geophysicist, so I can't tell you much more than that, but that's a great question. But they are good enough that they are widely used, so it is apparently good enough. Yes? Oh, so if you look at the compass, if you look at the center of the compass, you'll see that there's a weight that is pivoted, that has a degree of freedom relative to the needle. So that center weight, which is the magnetized part, is free to have whatever magnetic inclination it has, but the needle will be balanced just by gravity. So feel free to take a look at the compass afterward. Thank you.